the goat one, but okay. Install is launch, whatever. And then, of course, I have to thank Massimo, Roberta, and Gianluca. We did a very nice stay there in Mallorca, so I mean, there's that, and then there's me in Iceland. So, so the first part, I will show you a method. It's very simple. So, but it's nice, and I'll show you actually in an example of condensed matter physics. So there's that, and then I will show you, like, for example, how you can apply this method. So, as you know, like my PhD is mostly about applying graph theory approaches. So, so yeah, that's we have both like the same approach that we can use in condensed matter and in quantum information in extreme learning machine. And then, yeah, and then some like outlooks if you want to use it for your work. I guess it will be very straightforward as a concept, but is like a proof of concept in a sense. So what the approach, I call it complex network of correlations. And so the starting point is, as I told you, a very simple model, which is the transverse field Ising model. I mean, probably many of you know it very well now. What happened is that we have this Hamiltonian that shows in the ground state transition. We have a state which is ferromagnetic, which with a parameter, which is this G here, changes from ferromagnetic to paramagnetic. And there is a transition, which you can see by studying, for example, the 2-point correlation function defined as the following. So what happened is, I mean, you can study this in many different ways. But what was done in this paper, in these two papers, this is like the first one who shows this approach of the network of correlation, is to show this transition using network theory. So the network is based on the first paper. They've done it with mutual information, which was already showing to be an important metric for the transition, the quantum phase transition of the model. In the second paper, they studied also concurrence and negativity as a metric. But in general, you could have whatever kind of correlation metric you want. And the idea is the following. So you have like a chain of you have this chain of n qubits. In this case, they are qubits, but they also studied with Bose-Hubbard, but I think the qubits are the easiest one for everybody. The idea is that you take all the bipartition and you take each pair, for example, of qubits, and you compute a quantity. And this quantity, in this case, is mutual information. So what you do is you trace everything else, and you just keep one qubit, and you calculate the von Neumann entropy. Then you do the same for the other qubits. And then you do the joint von Neumann entropy of both qubits. Yes, are two different sides of the chain. And what you do is just calculate this metric, which is in this case is the mutual information, but in general can be different kind of metric. And you calculate the mutual information for each pair. This will build you a weighted network where the weights are all the mutual information. And then we can study what happens to this network. So these images are a little, I don't like them too much, but they are in the paper, so that's that. The idea is that, for example, here, that we are in in the paramagnetic phase. What we have is that the correlation is very strong with the first neighbors and the second neighbors, and then it dies off. So what happened in the network, that you will have this very strong nearest neighbor connection, and that could be shown, for example, as a ring network, okay, where all the links that connect in the middle are almost zero, while all the links that connect the chain in like a circular fashion are have different than zero weight. Yes. No, I think it's ferromagnetics. No, sorry, yeah, paramagnetic phase, yes. While in the other case, for example, which is the ferromagnetic, which is, sure. In the case that you have in the paramagnetic phase, what happened is that instead the network is different. So in this case, you will have like a ring. In this case, the network of correlation will be like almost uniform. Everybody will have long range correlation with everybody else, and you can show it with this methodology. So yeah, and of course you can study this also during the transition. So for each of different parameters. But what can you use? I mean, here I've put some like a table that can be useful if you want to use this this tool on how you can study this kind of networks with network theory. So this is super basic. The strength is like the degree. So this measure the sum of the mutual informations coming to a single qubit. And this, the meaning is how important is that node? So how important is that qubit compared to everybody else? And you can also study, for example, the distribution of the strengths and see if maybe there are a lot of important nodes or if they are all important at the same time. And there are many things you can study with strength. You can just also study the average to see what is the average mutual information that gets each qubit and things like this. I'll show. So the Fiedler value instead is something more, a little more complicated, not that much. L is the Laplacian of the graph. So I don't know if you know, like the graph can be represented as an adjacency matrix, which will in this case have the entries that are all the mutual informations. You can write the Laplacian, which is very simply connected to the. I don't show the definition because I think it's more useful if you, whenever you want to search it. It's just the degree, so the strength plotted as like put like as a diagonal matrix, subtracting and then you subtract the adjacency matrix. You calculate the eigenvalues. The first eigenvalue is always zero. Is always one for graph theoretic reasons, but the second eigenvalue is not, and this tells you how homogeneous is the network. It tells you that this network can be like if this is very close to one, is very homogeneous. If it's like more, it has more of a sparse structure, like cluster can have something like this. Similar, but computed in a different way, is the global clustering. And this also measure like clusteringness. So it tells you like it's the number of triangles compared to the number of triple points that are connected. So it's triangles versus like the open ones. And of course, with weighted network, it becomes a little more complicated, but the idea is this one. And this is also like a measure of clusteringness. And then there is density, which is actually a network, like it measures sparsity, because this one is the average, like the average links over the total amount of links that you have in the network. Like L times L minus 1 is the maximum amount of links you can have. And this measure how a link is important for the, like how all the links are important for the network. So it tells you if it's sparse or if it's dense. And then there is also another one, disparity, whatever. I mean, this one is just to show you that you, with the network of correlation, you can really see different kind of metric. You can use different kind of metrics to study different kind of things. Like if you want to see if your system, for example, has a transition that makes it all homogeneous, you will use, like, for example, feeder values. But if you, for example, instead want to study if one part of the system is how is important changes over time, you might select, for example, the strength and study the strength of the node changing your parameters, for example. And what they did in the article was actually studying the transition with the different measures. And they actually showed that what happens is that almost all of the metrics changes whenever you have this transition, so that the network changes widely. So you can see, like on the left, we have the ferromagnetic phase, and you will have Y, which measured the uniformity, means that at the left we have a very uniform network, and which is all connected between each other. And then on the right, after the transition, you have a more dispersed network. So they could actually see the transition without studying the ground state with this methodology, instead of looking at the correlation function, etc. Sure. For sure, it's absolutely, yes. They actually, in the article, I don't want to go too much into the detail. I want to just show you the method. In the article, they actually did finite size scaling also analysis, and they show that this is actually order parameter, and this is actually the derivative of the order parameter, because the scaling goes different with Landau theory. Yeah, so yes, but associating observables, I don't know, because it's yeah, but also like the mutual information, I don't know if it's an observable, but of all the links, but maybe yes, there's something you can associate. So they did it with matrix product states, and they did it, I think, for 20 to 100, I think, qubits, because it was easy to compute with the MRG. And yeah, so yes, also. But this one was to compute the ground states and then compute the network for each of the ground states. And the arrow here are system sizes, just because they also changed, as I said, the number of qubits. Okay, so now what I've done in Mallorca is applying this to quantum. So this one is a methodology you can apply wherever you want, wherever you have a transition, whenever you want to check, for example, I don't know, if the correlation in your system changes over time. What I've done in Mallorca is applying this to quantum extreme learning machines. So usual slide at the beginning of quantum extreme learning machines talk. Of course, I had to cite Luca. I promised him, so that's that. Yeah, so you have like data encoded in a quantum system in some way, or maybe the quantum system is already the initial data. Then you put it into quantum reservoir, black box. You don't know what to do, but it scrambles the data in some non-linear way. Then you have measurements, and from the outcomes, you will optimize a layer, classical, to get the desired results of the labeled data at the beginning. So at the beginning, you might have, I don't know, a quantum state and you want to reconstruct observables, or you might have, what I will show you afterwards is like, you will have like images and you want to do classification, which is what I did. So to took a database which is called MNIST. It's a database of images. And I did like a technique to decompose the image into a quantum state. The image is, we do what we call the dimensionality reduction. So the image is like a vector, a big vector of 784 elements. And we do singular value decomposition in this way. This is called the principal component analysis. And you take the first values, which are the most significant ones of the image. Because, you know, the image has a lot of blank space. It is not like, it's not everything is useful. So I took so it's 8 qubits. I took 16 components, so 2 times n components, and I encoded into the quantum state in this way. So these are the PCA components, 2 for each qubit. And yeah, and then what you do is, as I told you, you put in quantum reservoir. From the quantum reservoir, you take out probabilities in this case, and then you put it into a classical processor, which is in this case a one-layer neural network. So it's a classifying network, one layer, super simple. And yeah, what we found is actually, so as a reservoir, we tried some things, but what we ended up was using another thing, like an artificial kind of way of generating unitaries. What we devised was what I call artificially symmetric unitaries. It's not rocket science. It's like you take asymmetry defined as a Hermitian operator. You do diagonalization. What you will end up is like you have different eigenspaces depending on what kind of symmetry you chose. And from the block, you generate a unitary matrix inside the blocks, and then you rotate back into the original basis. And this generates to you a unitary randomly with the symmetry you chose at the beginning, like that commutes with S in this case. So by doing this, having this algorithm that generated the unitaries as reservoirs, we were able to test different kind of symmetry and how they affect extreme learning machine performance. We saw that, for example, har random is the best, of course, because it mixes everything up together. But also parity symmetry doesn't change a lot, because parity has 2 eigenspaces, -1 and +1, which has 2 big blocks, very big blocks. So it's enough for the reconstruction to scramble stuff enough. Ignore this one in the middle, were just a check. They were symmetry for rotation for each of the qubit of the same angle, but this is literally the same as parity. What happens is that it changes when we chose like symmetry for the sum of the spin, like for example the total excitation number, which instead has smaller blocks, and it lowered the accuracy. But who cares about the results? Like we tried the different kind of encodings, we tried different encoding bases. So what I wanted was to check if the network of correlation actually changed accordingly to the performance. And what I found out actually is that yes, we have, like for the image above is like is the accuracies, which we have 2 training and testing accuracies, while the image below is the network, of course on average on various repetition, is the network metric, the feeder value I showed you. And as you can see, so these are 2 different metrics. I put them in the same graph, but both show perfectly that the accuracy, when the accuracy decreases, for example, the feeder value increases, so the network shape changes. Before you had like a inhomogeneous network, and then you have a more homogeneous one. Why? We still don't know. We are looking for it, but still, the methodology is useful. You got lost? Okay. 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 Mm-hmm. 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 Before and after what? I don't. So like, I don't understand. So like I don't really want you to focus on what happens here, like what are the different kind of encodings of symmetry, etc. I want to show you that the single points that represent different kind of reservoir, for example, or encodings or whatever, have different associated different kind of states at the end. From the states, instead of analyzing the states, I analyze the network associated to the states. And I showed that the performance is as a correlation between the kind of network with the performance. So it's just like to show you the application of the method. Like I don't. Mhm. Okay. 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 I'll go back. The thing is that what I studied is you take your image, you encode it in a quantum state, then you evolve it, and then you will have a final state. I studied the network of this final state. The set of correlations between the outcomes. Yeah. Single qubits in the state. Yes. Oh, the network like yeah, the correlation network of the final state after the evolution. That one is the one that we are measuring, and then the motivation is that probably the shape of the network will reflect the kind of accuracy we have, like the kind of performance we have. We think that maybe if the entanglement is more dispersed, or the correlation in general is more dispersed, the network might, like the task might work better. While if your reservoir, for example, doesn't disperse entanglement well, then the task doesn't work. It's not like this one is just a way to encode the image in a quantum state. It's just you take the image, you do this dimensionality reduction, which will give you some numbers. No, the quantum state is deterministically created from the image. Like one image has associated one quantum state, and vice versa. So there is encoding. It's an encoding, yes. There is a task. I want to recognize something. Yes. Yes. But the process goes into I have an image. I encode this image in a sort of compressed way by PCA. Yes. Then I use this encoded state for in the reservoir. In the reservoir, let it on, and after that, I use it some classical operation. Yeah. To classify. To decode the information about the image. It's just to classify the image, because the image is from 0 to 9, and I want to know if that image is a 0, a 1, or a 9. Yeah, or, yes. So, and the network that you create is of the final state after the evolution. Before the evolution, it's a product state, so there's no correlation. Before is yes, okay. As should be. So yeah. So the rationale was, okay, let's change the reservoir, so we change, or the encoding, etc. So we know that we change the performance, and we want to see if the final state has a different kind of network structure of correlation. And what I showed was yes. Mm-hmm. That's your tune. Yes. There is no G. Like in that case, we had a G, and we showed that network changes. In this case, we have different encodings, different kind of unitary. You can have whatever parameter you want. Mine is not a parameter, it's like different kind. It's like instead of studying one parametric Hamiltonian, I studied this kind of unitary, then another. This one is discrete in a sense. Can you show us straight? Yes. Now, what are you comparing? So I'm comparing all different kind of unitary and encodings. They're all put together in the same graph. So one point is accuracy of system X. Doesn't really matter if the system like how it's done. This is, for example, symmetric with parity and encoded in the Z basis. But what I show is that this, like all the behaviors of the accuracy are reflected by the final state, in particular on the homogeneity of the network of correlation of the final state. You have concentrated whether you are no, sorry. I mean, yeah, I didn't say this, but because the accuracy is defined both for training and for testing, because you have a set of images, and some of them used for training. So, of course, if you tell, yeah, they perform better. If you put new images, they will perform worse. But doesn't really matter. But they are always one above the other in some way. But yeah, what I showed is that the network has, if you plot any, like almost any of the different metrics, they show the difference. So what I can see is that the network where QLM performs better is actually less homogeneous. Why? I don't know. I'm thinking still about it. If you have an idea, write me an email. But that's what I see. So it's actually also more sparse for some reason. I was thinking that it would have been the opposite way, but whatever. So yeah, at the end, I mean, hope you got the idea that you can use this network of correlation to characterize transitions, different kind of unitary, different kind of systems, and try to look into different type of metrics of your network to check what are the really what is really the physics beyond your problem, whatever it might be. And in particular, what I've done was applying this to quantum machine learning machine, such that I found that there is actually a relation. Still, I don't know what is in like a very rigorous manner, but for sure a relation with the performance. And I saw that all these the metric that in my use case was good was every metric that showed homogeneity of the correlations. Yeah, and then the idea is then to go to time dependence using quantum reservoir computing. So that's it. I'll leave with the page with Marco, and yes. Mm-hmm. Mm-hmm. Mm-hmm.
You use this for classical systems, nonlinear classical systems, because I don't know if you can define the transients in it.
I mean, in this case, what I studied is correlations. So I have like a metric that I can use for quantifying correlation for quantum systems. If you have classical spins, you can use other type of correlations. In general, yeah, why not?
But also for nonlinear
systems. I like. What do you mean for nonlinear systems? Sure. Sure. Of course.
At least you cannot define a matrix.
Okay, but you can still define a state of your system.
Yeah.
And you need just that. You need the state of your system, and then you compute the correlations. But yes, thanks for the question. Yeah, like a steady state. These are all done, for example, in the ground state. But maybe they could have also studied what happens on the first excited state. I don't know. I don't even know the transition in what happens in the first excited state. Yeah. Maybe nothing, but. Mm-hmm.
The intuition here is that the system somewhat, when you get closer to the criticality somewhat becomes rigid. Tends to get slower, everything becomes, which is related to the fact that things are more connected to each other.
Yes.
So,
yeah.
I have no intuition of what one should expect in the extreme reservoir computing.
Okay, it's more like the kind of unitary you use. If it works bad, it doesn't mix the data of the beginning. I mean, this is super very simply very simplified. There's Marco's article on that. So if you use like identity matrix, for example, which doesn't mix the data at all, that will be the worst case scenario. And that will show, for example, that your network at the end has no correlation. But if instead you use a hard random matrix, you will have everybody connected with each other in the last state. It will create this multipartite entanglement between all the qubits, for example. But it's still not super clear, in my opinion.
I would say maybe if you have a type of protocol in which you know that your protocol is for sure better than any classical protocol, you can do the same, or not. Also sampling.
Yes.
I mean, maybe here I can understand that that this type of procedure maybe can tell you something why your protocol perform better than classical.
Yes.
Have you thought of using
of course.
Quantum
yeah.
Machine learning.
Of course.
Machine learning, whether this proves that this type of operation is better than classical analysis.
No. I mean, in that case, like there's like it's a little hard to compare the best classical, Of course, if you have the very best classical classification algorithm perform better, but the classical classification algorithm with this approach might perform like the same. But for sure, if you have a different kind of problem, like boson sampling, for example, you can use your state of the system to check if, for example, the network of correlation has a particular structure that indicates, that might depend, of course, on the problem, that indicates, for example, that this task is better for has a quantum advantage, etc. You might have, for example, I don't know, tasks that are not are classically simulatable, and that you will have, I don't know, a network of correlation that has some properties. While if you have quantum advantage, then the network of correlation is different. Yes, I don't know if there is any work on this, because these two articles don't have a lot of citations, and they're mostly, for example, used. They have studied this in many body localization problems and stuff like this, but not. They have like 30 citations. So. Yes. Yeah. For example, for sure, yes. You might use just a part of your problem, and the one that you think is more important. Yeah, in general, yes. Of course, if you you have to be careful on what you are choosing to put out from your network, because maybe you are putting out the node that is strong, super strongly correlated with between other. Like, for example, I don't know, if you have one spin which is coupled very intensely to like a chain, you will know that this correlation is very strong. This one might be also strong, but like this one is not, for example. And then if you, of course, if you just focus on this, you will not see this, you will not see this. So yeah, but in general, yes. There's also like a graph theory approach where you can take like a big network and reduce it in the dimension, but that's another topic.
You know whether they also tested this procedure in other models?
I only saw many body localization, and I saw Bose-Hubbard models for sure, and I think that's that. Like, I've not seen anything like on photonics, for example. I mean, Bose-Hubbard is also for that, but yeah. Okay. Okay. Okay.
So essentially, okay, I'm not sure.
Okay. Okay. It's not the focus, in my opinion.
I applied this with it, and then I want to mix up the state. I went to final state, and then this final state, how do you get like the
Adjacency matrix.
and you get this
So you have rho. From this one, you calculate these ones, the ij, for each of the couples. So Si is just trace of everything that is not I of rho. Sij, I cannot write, is trace that is not I or j of rho. But for example, you could do concurrence. Like, you can trace everything that is not ij of rho, get a rho ij, and then compute the concurrence of rho ij. If the entanglement, the initial entanglement is very multipartite and very like is the starting state is very entangled, this one will be 0. But if the initial state is not strongly entangled, you will have like a complicated structure. Yeah, this one is a new, like a thing that I devised, I think, but it's stupid, but I could not find it in any other place. It's like you want a unitary matrix U that has some kind of symmetry. So you have a symmetry S, whatever it is, and you want to generate random matrices U such that they commute with S. So you do this procedure. You take S, take the diagonal matrices or all the eigenspaces. You get the indices of the blocks where the eigenspaces are. Like, for example, if it's the parity matrix, then you will have like 2 blocks. Yeah. In a machine learning machine, yes, because the more, like, if it's, as I told you, like if it's very, very symmetric, it will not mix up the qubits. Yes, but I wanted to get worse because I wanted to see the differences. Like it was a way to simulate interesting dynamics. Yes, for example, if we want to do this experimentally somehow. Yeah. Okay. So I guess there's that. Ciao Simo.